Okay, so in this video, we're going to take a look at how we can use pointers to refer to memory that's allocated during program execution. And this memory is also known as dynamically allocated memory. So let's get started. Alright, so if you remember from the video on scope, lifetime, and call stack, we had this diagram showing the memory layout. So anytime that we go and compile a program, the compiler is actually setting aside certain areas of memory for specific things. One area that's set aside is for our instructions, which is called the code or text area. Another area that's set aside is for our global variables, which is called the static or globals area. And then also we have an area set aside for basically all of the local variables, the return values, return addresses from each time that we call a function. So various functions are going to have their own variables that are defined within them and potential return values from those functions. So all that's done here in the stack, and that's what we talked about mostly in that video on scope, lifetime, and the call stack. One thing that we have not talked about, which is going to be a focus in this particular video, is making use of the free store or the heap. So this memory area here is what's left over after the allocation's been done for the globals, text, and stack area. So in the case of C++, we actually have to manage this area of memory. So whenever we're executing a program and we need to actually allocate memory dynamically at runtime, then it comes from this particular area here. But it is our responsibility, if we allocated any memory from this particular area, that we also go in and deallocate it as well. Okay, so in C++, the way we go about allocating memory on the heap is by using this keyword new. So we can say new and then specify some particular type. And the type could be anything. So it could be a primitive data type like a float, a double, an int. And it could be something from the standard template library like a vector, or it could be some type that we've defined ourselves in a class. So let's look at a specific example. So here we have new int. So what happens is we get space allocated on the heap, which I'll draw here in purple, for an int. So we have our heap here, and we'll have space allocated for an int. Now in terms of how much space that may be, it really depends. So different compilers, different processors would specify a different amount for an int. So in a lot of systems it would be 4 bytes. And we'll say that this particular int was allocated at address 500. In terms of the value that exists here, we really don't know the value particularly. So it's going to be whatever value existed there whenever we perform the new operation. So it's really a meaningless value at this point until we go in and actually override it with some particular meaningful value. But as it is right now, just with this new int statement here, we don't have a mechanism to actually go in and reference this particular int out on the heap. So let's look at and see how we could go and actually reference that particular int. Okay, so it turns out that not only does this new operation actually allocate space for an int out here on the heap, it also returns the address of where this int is located. So this address 500 is actually being returned. And so we know that if with a pointer, we can actually hold an address. So we said that a pointer is just simply a data type that holds an address for a particular thing, whatever thing that may be. In this case, it's holding an address of an int. So we could actually declare an int pointer, and that's exactly what we have here on the left-hand side of the assignment statement. We have int pointer p, so we're declaring a pointer of type int, and it's able to hold this particular address. So the pointer itself actually exists out on the stack. So let me draw a picture of the stack over here in blue. So we'll say that we have our stack here, just a different part of memory. And we'll say that, I don't know, maybe this line of code is actually in some particular function, maybe the main function. So we could in fact have other local variables that exist, but certainly we would have this variable p, which is a pointer, and it would hold this address 500. So that's exactly what's being returned when we do this new int operation, is this address 500. So we can imagine that p is now referring to this particular int out on the heap. Okay, so now that we have this pointer p that's able to reference this int out on the heap, we can actually manipulate what that int holds. So here on this next line, we have a dereference of the pointer p on the left-hand side of an assignment statement. So that just simply gets us to this particular int out on the heap and allows us to assign a value to it. So in this case, we're assigning the value of 5 to that particular int. So let me go ahead and update our int here to some meaningless value to an actual value that's meaningful to us, in this case the value of 5. Okay, so now that we're familiar with this operator new and allows us to create things out on the heap, let's go in and create a new int out on the heap. And this time we're going to initialize it to having the value of 10. So this operation here, or this third line of code that we have here, will just simply create an int out on the heap, and we'll say it has the value of 10. And we'll just make up an address here. Maybe it said address 700 in terms of where this space was actually allocated on the heap. And you can see on the left-hand side of the assignment operator that we've just reassigned our pointer p to point to this guy here. So again, the new operator returns the address, so it's going to return this address 700. So we need to update what p is pointing to here. So let me go in and update what we have p pointing to. So now we have p pointing to the address 700, and it is now referencing this particular int out on the heap. Now, what you'll notice is we still have our other int out on the heap here. So we have our original int that has the value of 5. Unfortunately, this particular int here is no longer accessible. So anytime that we've created something out on the heap, we've allocated some memory out on the heap, which we can no longer reference or no longer get to, this is what we call garbage. And garbage is a bad thing, especially if we're talking about larger programs where we may be allocating a lot of stuff out on the heap, so we're continually creating garbage maybe over and over again by some function call or something. Then we could run out of heap space. And whenever we run out of heap space and try to invoke the new operator and create something out on the heap, it could crash our program, or it would crash our program in those particular cases. This thing right here is garbage, and so we want to avoid creating garbage as much as possible. So now I'm going to show you how do we go about deallocating memory so we can prevent creating garbage out there on the heap. All right, so you'll notice here that I've changed up the code a little bit. So before we actually do this assignment operation here, what we should be doing is deallocating this int here from the heap. So we basically want to free up this space on the heap. So the way we go about doing that is by using this keyword delete. So we say delete p. And when we say delete p, it actually deletes what p is pointing to, or at least frees up what p is pointing to on the heap. So it doesn't actually delete the pointer p. That pointer p will stay there on the stack until whatever function this particular code is in actually terminates. At that point in time, then p would be removed off the stack along with any other local variables that we may have. So this delete operation here just simply deletes what p is pointing to. So we'll just show that this area of memory is being freed up. And now p is still pointing to that address location 500, but it's no longer a valid location in memory. So we wouldn't want to make use of p at this point in time, dereference it or do anything with it, try to assign a value to this particular address location. And this is what we call a dangling pointer. So a dangling pointer is just simply a pointer that no longer points to something valid on the heap. But that's okay. We're about to reassign our pointer p to that int value that we create out on the heap. So let me go ahead and create that int value that we had before. So here we go. Let me use the right color. So we'll create that int value out on the heap. And we said that the int value will initially have the value of 10. And we said that this was at address 700. So what we'll do now, after this operation has occurred, the new operator returns this address 700. So we'll have the value of 700 stored here. So let me go in and update the address here. So we have the address 700. And so we'll have our pointer now pointing to that new memory location. So we'll have this now pointing here. So that's basically what's going on. Whenever you want to do a reassignment, make sure a reassignment of a pointer from something out on the heap to something else out on the heap, make sure you're deleting what that pointer is pointing to before you go in and do the reassignment. I also wanted to note that if you do a delete operation on a pointer where you're freeing up this heap space here and you don't have something for the pointer p to be reassigned to straight away, then you don't want to just keep your pointer as a dangling pointer. What you should do is assign that pointer p to null. And so you can actually use null, or you can assign it to 0. It turns out that null is just simply a macro to 0, and it just simply indicates that the pointer is not referencing anything. So in this particular case here, if we did the delete operation, again, it frees up this memory out on the heap. And then what we would have is our pointer no longer dangling there. We would just simply have the value of 0 there stored for the pointer p. So if we were to try to make use of our pointer p, we would know that we have a null pointer there. It doesn't actually reference anything. So this is just good programming practice. Okay, so before I go and summarize some of the big ideas from today's video, I did want to discuss another way in which we could create garbage, and it's probably a more common way in which we could create garbage. So assume that main calls this function x. So we have function x here, and you can see that we have some code that we're somewhat familiar with in which we create a new int out on the heap. So we can imagine that a new int's created. Well, let me go ahead and create the stack frame really quick. So we have our stack frame here for x. So this is x's stack frame, and we have p that exists out here. And we're going to be creating this new int out on the heap, and maybe it's at address 500 since we've been using that address. Again, we didn't assign a particular value there. And what do we know? The address 500 is being returned, so we have the value of 500 that's going to be stored here. And so this guy references that. So everything looks good. The issue is, if we don't ever perform a delete operation inside of this particular function here, then we're going to end up having this thing left out on the heap, because whenever this particular function terminates, when x terminates, what happens? We end up having this guy being popped off, so the stack frame ends up being popped off, so all that stuff gets removed, but we still end up having our int out there on the heap, and nobody can reference it. So we just have created garbage here. So that's not a good idea. And that probably is a more common way of creating garbage than maybe forgetting to do a delete before a reassignment. They're both fairly common. All right, so let me summarize some of the big ideas from this video. We saw several new keywords, one of those keywords being the keyword new. And new was allowing us to allocate space dynamically on the heap. So it's often the case that we will not know at compile time what we may need in terms of memory requirements. So new is allowing us to dynamically allocate this space at runtime. And we also found out that new returns the address of the allocated memory. So if we allocated an int, whenever we use that keyword new, it returns the address of where that int actually lives out on the heap. So we can use pointers to reference that memory that's been allocated out on the heap. We also saw the keyword delete. So delete allows us to deallocate memory on the heap. So in conjunction with a new, traditionally you'll see a delete. If you don't end up seeing a delete, you'll probably end up with garbage. So garbage is created whenever we can no longer access previously allocated memory on the heap. If we go about creating enough garbage, then it could crash our program. And we also saw the idea of a dangling pointer. So a dangling pointer in and of itself is not a bad thing. So it turns out that anytime we do a delete operation on a pointer, we end up with a dangling pointer, and at that point we should be reassigning it to some other valid memory location, or we should be assigning it to null. One last thing that I'll say is that as you learn more about C++ and the standard template library, and you learn how to use the standard template library really well, then you can really avoid, in most cases, using new and delete. So if you use the standard template library, it goes about handling dynamically allocating stuff out there on the heap and then also deleting that stuff from the heap. All right, so that's it.